Uh, Yesterday we took a look at what functions look like and the characteristics of f of x and g of x. I'm away today, so this is how I'm going to teach you, and I have this put together for you. Hopefully this won't happen a great deal, but it's a great lesson to actually do that. It's quite short, and I should be able to get you going so that you can kind of take off on your own for the remainder of lesson 2 as well as lesson 3 as we get there. Now that we understand what a function is, we need to perform some operations. And the first operations that we're dealing with in terms of functions are the addition, the sum and difference of two functions. We do have these 4 operations that we have listed here, but we're only going to deal with these first 2 categories in lesson 2. Lesson 3, I'd like you to get on to the exploration and eventually explore product and quotient, but we'll discuss more of that next class. So we're going to deal with what f plus g of x means and what f minus g of x means. And from what we know of function notation and simplifying functions, really this means f of x plus g of x and f of x minus g of x, given that entire function f of x and that entire function g of x. To introduce ourselves to this concept, we're going to look at an exploration given 2 functions that we're not identifying the algebraic expression, but actually the listed values for f of x and g of x as given to us here. So what we're going to do is say, okay, if I know that f of x is -7 and g of x is -7, what is f plus g of x? And in this case, it's -14. The subtraction of those, f of x minus g of x, gives us 0. So we're going to continue on and finish this table of values, and we're going to get -11 and 1 and -8 and 2. And you can start to see that pattern emerging, and whether you want to finish the computation of f plus g of x or f minus g of x, you can do that as well. What I'd like you to do once you're done that, go ahead and pause the video or the lesson and complete this table and complete this graph over here on the right hand side. Graph f of x, graph g of x, graph f plus g of x, and then lastly f minus g of x. And you're going to get 4 different functions, and we're going to take a look at how those appear. So go ahead and pause it now, and when you're done, you can resume it, and I'll flip to the next slide. So hopefully you were able to complete this, and once you throw these 4 graphs on, you're going to get something that looks like this. So you've got your completed table of values for both f plus g of x and f minus g of x, and nothing revolutionary happens here. There's really no magic. We're adding and subtracting numbers, and synonymous with these 2 functions, once we graphed f of x and graphed g of x, we found that they were 2 linear functions. And when I'm adding and subtracting 2 linear functions, the result, as we see here with my orange line f plus g of x and my purple line f minus g of x, is again another linear function. One of the things to take a look at is maybe what the resulting slopes look like. Is there a relationship there? Is there something that I can draw a conclusion from the graphs, or are we just seeing that when I add or subtract 2 linear functions, I get another linear function? So that's really for you to explore and work with as we move on to kind of part 2, which is a similar exploration using quadratic functions. But before we do that, let's now look at the algebraic expression for f of x and g of x. We're given that f of x is 2x minus 2x plus 1 and g of x is x plus 3. If I graph 2x plus 1 and x minus 3, it would look exactly like these graphs denoted here by these values. Similarly, if we add them, f plus g of x, I should get 2x plus 1, and I'm going to add that entire function to x minus 3 to give me the function 3x minus 2. Oops, sorry, shouldn't be squared there. (3x minus 2). The subtraction, 2x minus x, f minus g of x should give me 2x minus x is x. Sorry. And 1 minus -3 is plus 4. And again, when we look back, the function 3x minus 2, that makes sense for f plus g of x, slope of 3 and approximately an x-intercept of negative 2, and f minus g of x, our x-intercept is 4 and we have a slope of 1. So yeah, those agree, those make sense for what we have. If you use your graphing calculator, I don't feel this is integral. If you want to, if you need practice with that, go ahead, you can throw them all on. If you go over to the left-hand side, you can actually change what they look like, but not an integral part of the activity. And again, domain and range, we know these are linear functions, and one of the characteristics of linear functions is that the domain is always denoted as x, such that x is an element of the real numbers, and my range is y, such that y is an element of the real numbers. So nothing exciting happening there. We should also be able to use these two functions to find f plus g of 10. We can look at what f of 10 is and g of 10 is and then combine them together by adding and get a result, or we can find this function f plus g of x and then substitute that in. So f plus g of 10 should be 3 times 10 minus 2, and again I'm just using this function here that I found for f plus g of x, and 3 times 10 minus 2 is 28. It's interesting that if I were to find f of 10 using my original function, 2 times 10 plus 1, right here, 2 times 10 plus 1 is 21, and g of 10, so 10 minus 3 is 27. If I added those together, I'd get 28. So we see that relationship between whether I have f of x and g of x, and then put them together to be f plus g of x. Similarly, and I'll leave you on your own to do f minus g of negative 10. Really, we're just plugging it into here, and we should see negative 10 plus 4 is negative 6. There's quite a neat step down here in h to solve for functions of degree 1, but they're not linear. Does this case ever happen that when I'm adding or subtracting two linear functions that my result is not of degree 1? And possibly the best scenario I can think of is what would happen if I had f of x being x plus 5 and I had g of x as x plus 1. If I add them together, I'm going to get 2x. If I subtracted them, x minus x, I'm going to end up with a line. This is of degree 0. Now it's still a linear function, and we define something to the power of 0 as being a linear function, but it's quite different because it's that flat line of g of x equals 4, or sorry, f plus g of x, or f minus g of x is 4. So it's a little bit different. Just something to think about in terms of these function operations. Part 2, another exploration, but we're dealing with the second category that we looked at yesterday. Yesterday we looked at linear functions, exponential functions, cubic functions, and then we also delved into absolute value and rational functions as well. So this is that second type, and we're going to do the same type of exploration with f plus g of x and f minus g of x, a little bit working backwards given the graph. So what we're going to do is work with these two values, and we have these kind of denoted points on the graph, and we're going to take this value and we're going to add it to this value. This is f plus g of x, right? This y value here being 24, and this one here at 21 or 22-ish. If we add them together, I get a plot that's right about here. Then if I take this one here and this one here, we're taking 12 and 6, and I add them together, I get 18. Continuing that process, adding these two here, 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 and we see this parabola occurring that looks approximately like that, adding all of those points, and it should kind of go down and touch the x-axis. So do this exploration on your own. I want you to pause it, go through, do both f plus g of x and f minus g of x, as well as answering each of these questions, and I'll kind of paraphrase them on the next slide here once you're finished. So pause the recording and do this exploration on your own. Okay, hopefully you're able to do that, and it ends up looking something like this. We have our two parabolas or quadratic functions, and we saw that when we add two quadratic functions or subtract them, they result in another quadratic function. And if we look at the algebraic expressions, we end up with these 3x squared minus 4x plus 4, as well as x squared minus 4, and these kind of match up to our graphs as well. And lastly, the domain and range, kind of an approximation of what we had on the graph. You could probably get a more distinct answer by putting them in your graphing calculator. I just kind of went with the exploration because there's nothing super important happening here. The one thing that I don't have on my slide that you probably do is there a time that occurs when I add and subtract these two functions that doesn't give me a quadratic function? And that is very possible. What happens if I have two quadratic functions that look like this? Y equals x squared plus 2, we're doing function notation, so we'll leave it in that notation. F of x equals x squared plus 2x plus 1, and g of x equals x squared minus 4x plus 1. If I subtracted these two functions, what's going to happen is these x squareds are going to cancel, and my result is going to be a composure of those, which is actually a linear function. So keeping that in mind, that this is not always the case, and we can't generalize to say that two quadratic functions are always going to give me a quadratic function when I'm dealing with addition and subtraction. That brings us to kind of our basic understanding of what the addition of two functions looks like, and now we just need to work through a few examples. So the first one being, if I have these two functions, f of x and g of x, what happens when I add them together? Really, we just need to collect like terms. We're collecting this x cubed and this x cubed, so it will give us 2x cubed values, negative 2x squared and negative 2x, so I have a negative 2x squared, and I have a negative 2x, and I have a positive 6 and a positive 6 to give me a positive 12. And I'll leave that f of x minus g of x for you. It's very straightforward. Okay, hopefully you got a chance to finish that. These following statements here, we can say that f of x plus g of x is a composition of functions. And it can be written as f plus g of x is equal to f of x plus the function g of x. And now I'm honestly not 100% positive if those are the exact blanks that go in there. But I'll leave you to do number 2 as well. Again, nothing super important occurring there. I think what they're looking for is probably this simplification here, this value to go there, just to be generalized, so you can do the same for number 2 here as well. What gets a little more important is what we have in C when we're doing some evaluation, and it's that multi-step synthesis that's going to occur. I'm going to leave one aside because I'd like you to give that a go, and we're going to do 2. If we have f minus g of root 6. So this is a great way to check what you've found before. Given that f of x is x cubed minus 2x squared plus 6, and g of x equals x cubed minus 2x plus 6, let's find f minus g of root 6. So f minus g looks like f of x minus g of x, which looks like this. X cubed minus x cubed. Actually, we'll just write out the whole function. oops, that's a minus. So these x cubed values cancel, x cubed minus x cubed. I get negative 2x squared minus negative 2x, so I have negative 2x squared. This becomes a positive value, plus 2x, and I have 6 minus 6, which is 0. So I have this resulting function of, let's factor it, negative 2 x squared, or sorry, we'll pull out the x as well. We'll pull out that negative 2 and the x. And I get left with x minus 1. So then when I'm finding f minus g of root 6, we know that all we have to do is put that root 6 in. So I have negative 2 times root 6, and then I have root 6 minus 1. So this can be just written as negative 2 root 6 and root 6 minus 1. Feel free to simplify as you like. I would probably think this is just fine because it's getting at what we're looking for you to find from the question. Last example, and we'll tidy things up and be done here. Let's put it into a contextual situation. It's a bit contrived given the basic values in this, but it's not a bad way to think about some of this function composition. So we have a multimedia company producing DVDs, which are $3 per unit, and the fixed costs, including the graphics, are $10 regardless of the number of DVDs produced. Each DVD retails for $15. If we know that we have some number of units produced X, let's answer the following in terms. So let's write a function for the total cost. We're thinking back to kind of math grade 8, 9 even to find this linear equation that represents this of the units produced. So our cost is $10 plus $3 per unit X per CD or DVD. We know that we have some value of revenue, R of X, and if we're selling them for $15, I'm going to get $15 for every value X that I sell. A profit for a company, it makes a lot of sense that P of X, my profit, is going to equal my revenue minus my costs. Fairly standard function, and in fact, as you move into hopefully next year, some of you will probably be taking some economics courses. You'll do a graphical analysis of this, and you'll see. Granted, they're very rarely linear equations like this, but a curved line that looks like here's the cost of producing something, and perhaps here's the revenue, and at some point those two things are break even. We call this a break even cost, and then we look for the differential between these two values here, and it really is this composition of functions where P of X is the revenue minus the cost, and this is right in Microeconomics 101 that some of you will see next year. Regardless, we have this function that we can say is R minus C of X, because we know about function notation, which is really 15x minus 3x, which is 12x plus 10. So not complicated math going on, just a great way to maybe perhaps remember what this function notation looks like. And if we produced 12,000 DVDs, it would be 20,000 plus, oops, sorry, this should be minus $10. We're subtracting costs. My fault there. We're going to subtract 10. They don't give us an extra $10 for making CDs. And that's going to be some result. And again, the number is not integral for that. So hopefully this worked for you. What I'd like you to do now is try some of the questions from here. I wouldn't do all 9, and I wouldn't spend too much time on the explorations because you've already done them. Make sure you understand how to add, especially the algebraic representations, as well as the addition, subtraction, and that third step of substituting. Once you feel comfortable with this, please move on to topic 3. we would like to get a good chunk of it covered today. Do the explorations for topic 3 and see what you can figure out about multiplication and division of functions. It's a very similar layout to this lesson, so you should be able to get well into it and get a decent understanding before we come back next class. If you have any questions, again, please make sure you send me an email or touch base with me later in the day. I'll be around, so come find me if you need to. Thanks, and again, let me know if you need anything.